I'm going to do a lab with this concave mirror. It's from a telescope. It doesn't have a lot of curvature to it, does it? Look at that. So what I'm going to do first is measure the focal length. Where does the light bulb have to go to measure the focal length? Really far away. See it right there? Way on the other side of the room. I got the mirror held up here with these two weights. So the light from the light bulb comes across the room, shines onto the mirror. The mirror is right here, and it reflects and goes to this piece of paper. I'm projecting an image onto the paper. If I move the paper further away, I get a larger spot. It's not focused. If I move the paper too close, I get a larger spot. It's not focused. I need to move it so that the dot is as small as possible. Right about there. Alrighty, I've taped the paper down so it doesn't move. And that's about 73.5 centimeters. That's how far the paper is from the mirror. Now I'm moving the light bulb inside this box. When the light bulb turns on, the box will cast a shadow on the screen behind it. The mirror is over here, and the mirror should project an image onto that screen if I've set this up right. Well, here we have it. There's the mirror, the bright light, and the image above it in the back. That's pretty clear. That's the light bulb. I can change the distance of the object to the mirror, and it changes how clear it is. I can focus it right about here. The DO is about 96 centimeters. Using the focal length, you should be able to calculate the DI, the distance from the mirror to the screen. Once you do that, we can check it out. We can measure that distance. 1 meter, 2 meters, 2.52 meters. How close were you? All right, let's go over the math. When the light bulb is far away, the rays come in parallel to the principal axis. They reflect through the focus. No surprises here. That's the normal lines. Angle of incidence equals angle of reflection. Now that's a concave mirror, and I didn't draw it curved a lot because in reality, it's not curved very much. If I extend the normal lines, they're going to pass through the center of curvature. It should be a parabola, but it's approximated by a circle. Well, then this line here is the radius of the curve. That's the radius of the curve. This is the radius of the curve. And approximately, you can see that the focal length is about 1/2 of the radius. So we found the focal length by moving the paper back and forth until we got a small spot there. That's where the focus is. And then we measure the distance from the mirror to here. I got 73.5 centimeters. Now in the next part of the lab, I put the light bulb with the arrow on it at about 96 centimeters from the center of the mirror. A light ray that goes in parallel to the principal axis goes out through the focus. In through the focus, out parallel. The image is going to be inverted, but will it be real? Well, we were able to project this onto a screen. There really is light here. Because we saw the image on the screen, it's a real image. Now we can use the formula to calculate the distance to the image. I get 313.6 centimeters. That's theoretical. Well, we measured it to be 252 centimeters experimentally. Where do you think the error might be? That's fairly substantial. It's probably in the focal length. To prove my point, just try plugging in 252 centimeters to the DI and go calculate a focal length. Not a huge error, but it's big enough to explain this difference. So a small error in your focal length could end up resulting in a very large error in your distance to the image. Now we can check out the height of the object and the height of the image. I get about 3 centimeters for the height of the object. Using hi-ho equals negative di-do, we have 3 centimeters for the height of the object. The distance to the image, I'm going to use 252 centimeters. That's correct. That's exactly what I measured. And the DO is the distance to the object. That's going to be 96 centimeters. That's what we measured. And now I'll calculate the HI. And I get a negative 7.9 centimeters. Why negative? It's upside down. Now let's see how it really looks. All righty, it's all set back up again. And there's the image. Now that might be hard for you to see, but it's about 8 centimeters. That's pretty darn good. Well, this mirror was not curved very much for a telescope, but some mirrors we use are very curved, like this flashlight. Look inside it. It's parabolic. What's going on with that? Well, here we have the parabolic mirror. Where would you want to put that bulb? Watch what happens when we put the bulb at the focus. Light rays that spread out are going to hit the mirror. They'll be reflected parallel to the principal axis. Hey, that's the whole idea of making a beam from a flashlight. It's parabolic so that we can put the bulb well inside and capture most of this light and reflect it this way. Can you see how far inside the bulb is? It projects most of this light straight ahead. All right, here's another example of a mirror that's curved a lot. This is convex on that side, concave on this side. Look what happens when I put my finger inside here. The image starts to come out at you. Hey, listen, in real life, this looks pretty 3D. It's very, very cool. Now, what about this one over here? That's convex. Everything appears smaller. It's all virtual, and it's behind this mirror. You can use this in a store. Keep an eye on customers. Security mirror. You can also put it at the end of a driveway so that when you're backing out, you can see what's coming around the corner. Sometimes we do have mirrors that, even though it might be a distorted image, we want them curved a lot.